All right, Advanced Math 8, welcome back to second semester. We've got lesson 6.1.1. We're going to work with multivariable equations. All right, so last semester we looked at the big race. So here we've got the big race again. Georgia's going to join the big race. Her race can be modeled with the equation y equals 3x plus 4. Remember, x is time, and then y was the distance in meters. So we want to know what kind of head start did she get? What we found out last time was the plus 4 was the head start. So she got a 4-meter head start. Now we didn't have to find it that way just by looking at it. We can think of it in a different way. We can say, well, her head start would be when the time is 0. So if I plug in a 0 for x, I get 3 times 0, which is 0, plus 4, 4. So the distance is 4 when the time is 0. So we could also look at it, in that way. The next part is, what was Georgia's rate of speed? So the rate of speed is our slope. And here we're comparing, remember the slope is the change in the y divided by the change in the x. So when it says 3 for the slope, this is saying 3 of the y's, and y's are meters, for every x, which is time, so meters per second. All right, so when we have it in that format, we've called the slope-intercept form, everything's very easy to see because we've got our slope right here, we've got our y-intercept right there, everything we need is sitting right there in that form. Okay, so that problem is in slope-intercept form, y equals mx plus b. But what if we were given the equation in a different form, a form that is not y equals mx plus b? So here we've got an equation that's called standard form. Standard form is when the x and the y are on the same side of the equation and they have coefficients with each of them. So this is standard form. Okay, what would be the slope and the y-intercept for this one? This is just where you make kind of a guess. What do you think the slope should be, and what should you think the y-intercept would be? You might look at it and go, well, the slope was usually the number in front of x, so I think the slope's going to be negative 6. And the y-intercept was just kind of the integer by itself, so maybe the y-intercept is 10. You'd be wrong, but that'd be a good guess based on what we've done before. But since this is in standard form and not slope-intercept form, we can't just get the slope and the y-intercept automatically. There's no quick way to do it with standard form. So what we're going to do is we're going to try to work this out and see what the equation should have been. We're going to look at a table, we're going to graph it, and then we're going to use algebra to actually change this standard form problem into slope-intercept form. So the first thing I want to do is make a table. So when x is 1, we want to find out what y is. So I'm going to plug in 1 right here. So this would be negative 6 times 1 plus 2y equals 10. So this would be negative 6 plus 2y equals 10. I'd add 6. I get 2y is equal to 16. Divide by 2, and y is equal to 8. So 1, 8 should be a point on our graph. So let's go over here. 1, 2, 3, 4, 5, 6, 7, 8. There's 1, 8 right there. That should be a point on our graph. Now we'll plug in 2. So we'll do negative 6. Instead of x, we plug in 2. Plus 2y equals 10. Okay, so this is negative 12 plus 2y equals 10. Add 12 to both sides. We get 22. Divide by 2, and we get y is equal to 11. So when we plugged in 2, y was 11. The last thing we want to do is plug in a 3 for x. So you're going to do negative 6 times 3 plus 2y is equal to 10. So this is negative 18 plus 2y equals 10. Add 18 to both sides, you get 2y is equal to 28. So y must be equal to 14. Okay, let's graph these other two. So 2, 11, so this was 8, 9, 10, 11. and then 3, 14. This is 11, so 12, 13, 14. All right, then we should expect, since we have a slope is increasing by 3 and then going over 1, so 3 over 1, we can go down 3 and backwards 1 to find our y-intercept. So what's our y-intercept? Our y-intercept is 5. What's our slope? It's going up 3 and over 1, so it's 3. So it's not a slope of -6 and a y-intercept of 10. It's a slope of 3 and a y-intercept of 5 instead. So now we want to just go ahead and do this algebraically to show that that's what it actually is when we put it into slope-intercept form. So we're going to start off with -6x plus 2y equals 10. To put it into y-intercept form, we want to isolate y, so get that by itself. So since this is -6x, I'm going to add 6x to both sides. That leaves me with 2y equals 6x plus 10. Okay, y is not isolated because this is 2 times y. So the opposite of multiplication is division. So I'm going to use my division property of equality. Now, the division property of equality says I have to divide both sides by the same number. So if I divide this side by 2, I have to divide this entire side over here by 2 as well. So the 6x gets divided by 2 and the 10 gets divided by 2. That's the division property of equality, both sides. You can't just pick and choose what gets divided by 2. Everything gets divided by 2. So we get over here, y is equal to 6 divided by 2 is 3, so this is 3x, and 10 divided by 2 is 5. Now we have the equation that was in standard form into slope-intercept form. And look what we got here. 5 is the y-intercept. That's what we got here when we made a table. The slope is 3. This goes up 3 and over 1. So we can see now that our graph is matching the slope-intercept form. And there's our line. So for graphing, slope-intercept form is probably the best form to use. Standard form is used for other things, and we'll get into that later. But just for now, know that if we are going to graph something, we probably want to have it in slope-intercept form. So if we're given something in standard form, it's probably better to change it to slope-intercept first before we start graphing it. We can see that this whole process took a little bit longer. We got the same graph, but we had to do a whole bunch of math in here. Whereas if we just put it in slope-intercept form, we could find the y-intercept and the slope right away. All right, next we want to rewrite the following linear equations into slope-intercept form. So that means we're going to isolate the y and then put everything else on the other side. That's what isolating means. So looking at this one, let's see. Here's the y. I want to get it by itself, so I'm going to subtract the x from both sides. So that's going to leave me with 2y on the left side. Over here, these are like terms, so I can combine them. 3x minus x is 2x. And then I can use the division property of equality and divide everything by 2. So I end up with y equals 1x, or just x, plus 2. So the slope is 1, the y-intercept is 2. Not as easy to see that when it wasn't in slope-intercept form. All right, next one. We've got y's on both sides. So I want to combine the y's onto the same side. So I'm going to subtract 2y from this side and subtract 2y from this side. Okay, so on this side, I now have y plus 2 equals negative 5x. Okay, I have an isolated y. It still has a positive 2 over there, so I'm going to subtract 2 from both sides. So on that side, I'm left with y. On the other side, these are not like terms, so I just write it as negative 5x minus 2. So my slope is negative 5. My y-intercept is at negative 2. All right, next one. Okay, there's a lot of different ways you can do this. You could distribute if you want to. But notice how both of these two terms over here are even. If I divide by 2, 2 will go into them evenly. So I can, if I want to, just say, hey, let's divide this side by 2 and divide all these by 2. So then these 2's would reduce. I'd get y minus 3 equals 2 over 2 is 1. So x minus 3. And then I'd add 3 to both sides. And I'd get y is equal to x. So my slope is 1, and my y-intercept is 0, because there is no number over there. Now, if you would have distributed first, you would have gotten the same answer. So as long as you're using your properties correctly, you can get multiple pathways to getting the correct answer. All right, next one. Now this one, I'm probably going to go ahead and distribute over here. I've got distributing on both sides, so it doesn't make a lot of sense to me to just try to divide by 2 on both sides or whatever. I'm just going to distribute both sides. So I've got x, and this is a negative 1 times y, so that's negative y, and negative 1 times 2 is negative 2. On the other side, 2 times 2x is 4x, and 2 times 1 is 2. Okay, I need to start moving everything over to the other side. I'm going to subtract x from both sides. And while I'm at it, I'm going to add 2 to both sides. So I subtracted x and added 2 to both sides of the equation. Over here, I'm left with negative y because the x's canceled and the 2's reduced themselves. Over here, I'm left with 4x minus x is 3x. And then 2 plus 2 is 4. Last thing I'm going to do, this is negative 1 times y, so I'm going to divide everything by negative 1. Can you multiply everything by negative 1? Sure, why not? Okay, so negative y divided by negative 1 is positive y. 3 divided by negative 1 is negative 3. And 4 divided by negative 1 is negative 4. So my slope is negative 3, and my y-intercept is at negative 4. All right, we are really moving now. Next page. All right, so 6.4 says, how many solutions does 0 equals 3x minus 5? There's only one variable there, and I can easily solve that. I can add 5 to both sides. And I would get 3x equals 5. Then I can divide by 3 on both sides, and I'd get x equals 5/3. That's the only answer that x can be. So there's only one solution. One variable means there's usually only going to be one solution. Now, however, on this next one, I've got y equals 3x minus 5. I've got 2 variables in this one. So how many solutions do we have here? We've talked about this before. We know that there's an infinite number of solutions. I can just keep on plugging in a different number for x and getting a different number for y each time I do it. So I can just keep on plugging in whatever number I want. So this is an infinite number of solutions. Infinite number of solutions. Because you plug in 1 and you get negative 2. You plug in 2 and you get 1 for y. So these are all solutions. Now, how could we show these solutions? Probably the best way to show all the possible solutions is to make a graph. That's what graphs are good for, is showing all the solutions. So graphing shows all the possible solutions. You'd be asking yourself, all the solutions? Really? Does it show all of them? Yes, it does, because those arrows that we did here on this last graph mean it goes forever. That's showing all the possible solutions because these keep on going forever and ever and ever. All right, so here we've got something a little bit different. We've got a cubic graph. we've got y equals 0.2 x to the third minus 5. How many solutions are there? There's two different variables. So like that previous one, there's going to be an infinite number of solutions. Because I can keep on plugging in an x and getting a different value for y. Is forever, basically. And so that's what this graph is showing. It's showing me all the possible solutions. So based off of this, does it appear that 5, 8 is a solution? Well, if 5, 8 is a solution, then this graph would go through 5, 8. And let's see, it's going by, looks like it's going by 2's in this direction and going by 5's in this direction. So 5, 8, this would be 1, 2, 3, 4, 5, and then 8. 5, 8 would be about right there. Is that on the graph? No, it's not on the graph, so therefore it's not a solution for the equation because the graph represents all the possible solutions. So we can say, no, the point is not on the graph. All right, explain how we can estimate the solution of 4 equals 0.2 x to the third minus 5. All right, well, this kind of comes back to what we've been talking about before, is that these are solutions. Now, 4 is the y value. So where is 4 on the y-axis? Well, in this case, it'd probably be about right here. That's 4. So let's see where it passes through at 4. Looks like about right here. That point right there has a y value of 4. So now all we want to do is find out what that x value is. So if I go down here, the x value would be 3. I don't know, I'm going to call it 6, 3.6-ish. That sounds good to me. I'm going to say that it's about 3.6 because we're estimating here. So we knew that the y value was 4, and then if we look here at 4, the x value is about 3.6. I don't know if that's the exact answer, but it's close enough. Looking at the graph, we can estimate, because we're not telling the exact answer, we're estimating. And so when the y is 4, we think that the x would be about 3.6. And we can do that by looking at our graph over here. All right, next we've got formulas. And we want to just solve for different formulas. A lot of times you are doing a formula, but you don't want, like this one's the formula for work. Work equals force times distance. So what if we weren't looking for work, but we were looking for force instead? Well, how do we solve for F? That means isolate. Anytime it says for and then the variable, we're going to isolate. So in order to do that, we're going to do our properties of equality. Now this one says that force times distance equals the work. So if I want to isolate force, I need to get rid of distance. And since it's force times distance, to undo that, I'm going to divide by distance on both sides. So now the distances cancel over here. I find out that force equals work divided by distance. Over here, this is the conversion from Fahrenheit to Celsius. Okay, so if you've got a temperature in Celsius, you can plug it in, like that they use like in Europe, well, basically everywhere else in the world. And you want it in Fahrenheit like we do here in the States. Well, what you can do is plug in the number for Celsius, plug it in, work it out, and then you'll find out the Fahrenheit number. But what if we want to solve for Celsius instead of solving for Fahrenheit? Well, we need to start undoing things. Now, you could multiply by 5 first. But if you do that, remember, you can't pick and choose what you multiply by 5. by. So you'd have to multiply Fahrenheit by 5 and 32 by 5 and this by 5. So instead of doing that, I'm going to add 32 to both sides first. Usually when you do these problems, you want to do the addition and subtraction first, and then do your multiplication after that. So here I've got Fahrenheit minus 32 plus 32 is equal to 9c over 5. Okay, now two things are happening with c here. I'm multiplying by 9 and I'm dividing by 5. Now I can get rid of those at the same time by multiplying by the reciprocal. I can multiply this side by 5 over 9, and then the 5's and the 5's reduce here, and the 9 and the 9 reduce there. So I can multiply both sides by 5 over 9. And then we would find out that Celsius is equal to 5/9. And remember, we're multiplying by all of this, so I'm just going to put this in parentheses, F plus 32. So now if I know it's 100 degrees Fahrenheit, I can plug in 100 here and find out how many degrees that is Celsius. So I'd do 132 times 5/9, and then that would give me how much 100 degrees Fahrenheit is. All right, next one. What is that, rho? Equals mass divided by velocity? What is rho? I can't remember. Anyways, that's the Greek letter rho, I believe. And we want to do mass. So this is mass divided by velocity, I think. So to get rid of dividing by v, we'd multiply both sides by v. So we'd find out that m is equal to rho, and it looks like a p, but it's rho, times velocity, or we could just say rho times v, rho v. All right, last one. Solve for the indicated variables in the equations. We want to solve for y. Well, let's look at this first. I think we can simplify a little bit of this. Here we got y to the 0 power, and we should know by now that anything to the 0 power is 1. And over here, I've got a negative 2 exponent. So that means that I can change that to x to the second. And now to get y by itself, all I have to do is subtract 1 from both sides. And I get y equals x squared minus 1. Next one, I've got distance equals, well, this is like a current problem, rate plus current or something like that times time. So if I want to get t by itself, right now t is being multiplied by r plus c. So let's divide by r plus c. So now these two would reduce each other. So we're just using opposite operations to move things around. So since we're multiplying by r plus c, I divide both sides by r plus c. So then we'd find out that t is equal to d over r plus c. Next one. Okay, so here we've got two binomials being multiplied. So I should probably multiply that out first. So over here I've got x squared plus 4y, 4y equals x plus 6 times x minus 2. I should get x squared plus 4x minus 12. And basically I was just doing in my head the area model that we learned before, where we had x plus 6 over here and then x minus 2 over here. This is x squared, 6x, negative 2x, and negative 12. And these two are where I'm getting this 4x from. All right, I can subtract 4x, or subtract x squared from both sides. And I get 4y is equal to 4x minus 12. I'm trying to get y by itself, so I'm going to undo this multiplication. So the opposite of multiplication is division, so I divide by 4. Everything gets divided by 4. And I get y equals x minus 3. And now y is isolated. All right, last one. Let's see, we want to get x by itself. So I'm going to distribute here first. I'm not going to divide by 3 on both sides because I see that these two numbers, 3 won't go into evenly. So I'm thinking I'm not going to do that. So I get 6x plus 12 is equal to 2 plus 6x plus 10. I subtract 6x from both sides to get them together. Ooh, I get 12 equals 12. Looks like my x's are gone. So what happens when 12 equals 12? Well, how often does 12 equals 12? It's always equal to that. So this is infinite solutions. All right, so basically we're just using our properties of equality, adding a number to both sides, subtracting a number to both sides, multiplying a number to both sides, dividing a number by both sides, all of our properties of equality to move things around to get our variable by itself. That's all I've got for you. Enjoy. See you later. Bye-bye.